that we can start with the talk of Pawel Caputa on complexity and bulk momentum.
Okay, thank you, Tuan. So welcome, everyone. I would like to start by thanking the organizers for inviting me to this great event and giving me the opportunity to share some recent interesting story. And indeed, I'll tell you about the relation between the quantity called spread complexity and the bulk momentum in ADS-CFT. So I'll first give an introduction and short motivation for this work. Then I'll describe what the spread complexity is. And finally, I'll go into the relation between this quantity and the bulk momentum in ADS. And I'll finish by discussion and open questions. And this will be based on work that should appear soon with Bo and Chen, that was a postdoc in Warsaw and is now moving to Beijing. And also Ross MacDonald, John Simon, and Ben Streetmatter from the University of Edinburgh, as well as previous works with my excellent collaborators Vijay Balasubramanian, Javier Magan, Sinong Liu, Dimitris Patramanis, and Qingye Wu. Okay. So let me start. Over the last decade or so, by now, you've been bombed on arXiv by various statements that complexity equals to something. And maybe some of you have seen that from already from 2014 that it was the volume or it was some action on the specific Wheeler-DeWitt patch. And lately, there might be an even more general statement that this complexity in holography is almost anything. But the main statement about this is that people have been computing various observables on the gravity side, and these observables probe the interior of black holes by either kind of directly measuring the size of the wormhole or black hole interior in some specific holographic way or gravitational way. And the hope is that this very fine-grained observables should correspond to some notion of complexity, I put it in quotations here, of dual state in ADS-CFT that describe these geometries. And if we understand this complexity, then we can look at the time behavior of it or its particular growth in holographic models. And then hopefully we can learn something about these black hole interiors or singularities and so on and so forth. And this has been going on for, as I said, for already 10 years, but it's still a very active subject of research both on ADS and on CFT. And in my talk today, something disappeared. Oh gosh. It seems like my slides are not showing correctly. Yeah. I checked the ones that I sent were okay.
I'm not sure what I can do.
Can I quickly plug my laptop?
You can
No. I'm really sorry for this. Yeah, and this is the PDF I sent. Can I just plug it? Yes.
Do you have a connector? Or
yeah, I do.
No, let's just try to do it. Just wait a moment till I change the okay. You need to change the display settings.
Maybe if I just...
Can you get to the...
Oh, yeah. Okay, and then a view. And full screen. Sorry. Oh gosh. Sorry, maybe I just.
Oh, that's you. Let's do the green there. To make it great, then that should be close enough.
I cannot see it. How do you do it?
On the left is green flashlight.
Yeah. Sorry.
The cursor.
So maybe I just
There
open.
you go.
Okay. Okay. I'm really sorry for this. Okay. So the story I was going to tell you about today is actually maybe a corollary to some of these developments, namely the relation between the complexity and the momentum. So basically, this was noticed a little bit later than the original works, but also in a series of very interesting papers by Lenny Susskind, but also Lin, Mal, Sena, and Zhao, and also followed by Ling and Zhao, that if we study a complexity, again, this time not of state, but of some time-evolved operators, and if we quantify this complexity by a size, then there should be a dual picture of this operator growth. For example, by exciting some state with some local operators, we could describe it as some momentum, as some particle that moves from the boundary into direction of into the interior of a black hole spacetime. And basically, if we compute, the question would be there: how do we quantify this size or the complexity of the operator in time from the perspective of this particle in the bulk dual? And they propose that if we compute the radial momentum of this inflowing particle, there should be a relation between the growth of complexity in CFTs and this radial momentum of the particle in the bulk. Okay? But actually, when we discuss all these proposals, the first question that one usually gets at seminars and talks is, of course, what do you mean by this complexity? Is there some notion that actually, this picture look very interesting and inspiring, but is there really some notion of complexity that you can compute in some meaningful holographic theories that would match this gravitational prediction? And this is what we've been doing for the last several years with a bunch of people in our field. Namely, we're trying to come up with a useful and a good definition of operator size and complexity of states in many body systems as well as in quantum field theories, and then apply them from the perspective of this holographic from this holographic object. And one definition that I will be talking about today is the so-called spread or krill of complexity, which has a very simple idea for quantifying the dynamics or evolution or complexity of dynamics or evolution of the states. And the idea is as follows. Basically, we start with some quantum state psi or some simple operator at some initial time, and then as we evolve them, we can look at this evolution as the spread of states or operators in Hilbert space. And then we can map this evolution, this kind of diffusive evolution in, let's say, generic system, to a one-dimensional chain where basically at each side of the chain, basically where you are at this chain quantifies roughly what is the complexity of the state or the operator at a given time. I will make it very precise in a moment. And so basically this is the idea. We map the unitary evolution into a one-dimensional chain, and then we quantify complexity as the distance from this origin of the chain, where the origin represents the initial state or the operator at time 0. And the whole kind of name of this story and the key concept in this measure is the so-called krill of basis. I will explain this in a moment what it is. And basically the expansion of the state or coefficients of this expansion of the state allow us to map this dynamics or capture the dynamics by a certain probability distribution given by the square of this coefficient. And once we know this probability distribution, then we know everything about the quantum dynamics of this initial state or the operator under Hamiltonian H. And we compute this spread complexity or Krylov complexity, that's why sometimes it has letter K, as the average position on this chain as a function of T. Okay, this would be my definition. Good. So maybe a little bit more technical. What we actually do is basically we start with the state psi 0. This is our initial state, maybe simple or complicated, and we pick a Hamiltonian H, and we perform the formal expansion of this state of our interest in power series of T. Okay, and that leaves us with a set of state psi k that can be written as simply for different powers of time as the initial state psi 0, then at the first power of time as the Hamiltonian acting on the state 0, and the second 2 Hamiltonians, and so on. And this is the so-called Krylov subspace that probably many of you are very familiar with algebra and so on. And then, in general, this Krylov subspace is not orthogonal, not orthonormal as well. And what we want to do is we want to find a basis on this subspace, the so-called Krylov basis, that allows us to interpret these coefficients as probability. And this is basically done by your favorite Gram-Schmidt orthogonalization applied to this Krylov subspace. It has a fancy name, so-called Lanczos algorithm, where we basically do it recursively, step by step, starting from n equals to 0 up to some particular value of n, where and basically the algorithm goes as follows. So the initial vector in this expansion, k0, k with label 0, is always the initial vector psi 0 from which we start with. And then we first construct a vector, for example, a1, that will be a Hamiltonian applied to the vector k0. And then we subtract, we introduce a set of so-called Lanczos coefficients that they make sure that this state is orthonormal and orthogonal to the previous one, and so on and so forth. So this way we construct this basis. And these Lanczos coefficients that play the crucial role, they are so-called the Lanczos coefficients an and bn. They are defined as an expectation value of this Hamiltonian in the Krylov basis vector kn, and the bn and Lanczos coefficients are just norms of these vectors an. Okay, and you do this procedure recursively, starting from this initial state, and you stop at the point where your coefficient bn becomes 0. Okay, this means that you have already constructed all the vectors to represent the time evolution of the state, and that's it. And basically, this Lanczos algorithm not only leaves you with the Krylov basis Kn and the Lanczos coefficients, but also puts the Hamiltonian into a special form that allows to fix now these coefficients of the expansion of the state in the Krylov basis. And basically, you fix them by the so-called solving Schrödinger evolution equation. When we basically take this time derivative of this coefficient, we bring down the Hamiltonian, and then we apply this the definition of the Lanczos algorithm to write what the right-hand side would be. And we need to solve this Schrödinger equation with initial condition such that at time t equal to 0, we are basically at our initial state psi 0. Okay? And as you see, that solving this equation requires, of course, it has two very crucial ingredients, namely the initial condition, but also these Lanczos coefficients, an and bn, and they can be actually extracted directly from the moments of the so-called return amplitude. So basically, if we know the evolution of the state psi of t and we project it at state psi of 0, so this is the probability that you do the evolution but nothing happens. If you know that probability amplitude and you expand it in powers of t, you compute the moments, there's a very nice algorithm to extract Lanczos coefficients ans and bns from it, and then compute basically from the moments, from these two ingredients, you can compute this probability distribution Pn of t, and you can compute the Krylov, the spread complexity as a function of t as an average position n in this probability distribution. And this has already been very useful in lower dimensions. Actually, this approach, the Krylov basis approach, and it was noticed in very nice works by Berkus and company, that actually, and also later by Henry Lin, that in JT gravity, or in kind of going to that JT gravity from from the double scaling limit of SYK, one can show that the Krylov basis is a very natural basis for computing correlators or moments in the thermophile double state of that model. And then it was later used in a very nice paper by Rabinovici and collaborators, including Julian Sonner and his postdocs and students, where they showed that actually this Krylov complexity can be really matched with the length of the wormhole in JT gravity, and also, at least for some values of time, it also matches the prescription on the gravity side. So basically now, the question I want to ask here is that now that we developed a precise definition of complexity in quantum many-body systems in CFTs, can we finally make progress on this holographic complexity, let's say in higher dimensions? Can we understand better this proposal between holographic complexity and momentum? Can we actually make some qualitative matches there? Because I didn't mention, but actually these definitions of complexity, they became actually since they are very concrete and kind of computable for any interacting many-body systems and quantum field theories, they kind of got a different life, and people started using them beyond the holographic, but we wanted to bring them back to our discussions and see whether we are finally in a position of saying something interesting about complexity in holography. So first of all, to make the discussion more quantitative, what we want to do is we want to first define a very specific setup where we can really study some evolution of the operator and its relation to some point particle in the bulk of ADS. And this has been done in some older works that comes under the name of local operator quenches in ADS CFT. So let me clearly describe you the setup. Basically, we start from some initial state. This can be a vacuum. Then we pick a primary operator O inserted at some position X. And then for the state to have a finite energy, because of uncertainty principle, we need to smear this operator O of X with the Hamiltonian and in some Euclidean time epsilon that we keep finite. Okay? Basically, what the smearing does is that the energy of the initial state is finite and is fixed by the dimension of the operator over this smearing of the operator epsilon. So this is the thing that will keep finite for our evolution. And then we perform time evolution of this initial state, we normalize it, and we can study various observables and quantities in this state. So for example, there has been a lot of work on correlation functions and entanglement entropies under the local quenches back in the days. And actually there has been a series of very interesting papers on trying to understand these local operator quenches from the gravity side, and the model actually that was proposed and tested to a very high precision was basically a moment of a point particle with mass m times ADS radius equal to the dimension of the operator, and this point particle at time t equal to 0 start at the boundary at the value z equals to epsilon, which is exactly the map between this operator smearing cutoff and the epsilon. And this point particle is described by just a usual massive point particle in ADS action. This example is in ADS Poincaré, but the particle just follows this trajectory that the t equal to 0 is just at the boundary and then goes t square away from the boundary at fixed a towards the interior. And a very similar model has been generalized, for example, for taking the thermophile double state and inserting, for example, a left operator on the left side, and normalizing it again, regularizing it again with the left Hamiltonian and shooting this operator back into the bulk. And then we tested quite extensively the bulk picture of this, where the operator from the left side goes to the boundary in the, for example, in BTZ coordinates here on the left boundary. You can find the trajectory as a function of the inverse temperature beta that is related to the mass of the black hole this way, and as a function of time and as a function of epsilon. And you can see that basically after the time of order beta over 2 pi, the particle reaches from the boundary towards the near horizon region and then basically stays there for a long time because the operator from the external boundary cannot see it. But basically, in this setup, we really have at least we can really now start with a setup where the picture of Lenny and collaborators between the point particle in the bulk is now well described by this local operator quench in the CFT. Okay, at finite temperature, at finite size, and also at infinite line I'm drawing here. So the question we want to ask is that, okay, now that we have this, the computation that we would like to do is basically we would like to compute the picture that we would like to do. Okay, I'll call this. The picture, the computation that we would like to do is basically starting from this initial state, let's either at finite temperature or finite size or zero temperature, we would like to compute the spread complexity of this particular state, and we would like to check whether this has anything to do with the momentum of this particle in the bulk. Okay? And indeed, I told you that the main objects that we need to use to extract these Lanczos coefficients and compute these probability distributions are the so-called return amplitudes. And in all these three computations that I outlined, they basically correspond to certain regulated two-point functions of operators, either on the black hole background or in the CFT on the cylinder or CFT on the plane. And we have done this computation already in the past, and we can easily compute analytically these Lanczos coefficients for all these three cases and extract the probability distribution. It's a bit complicated, but at the end, it's governed by certain symmetry, so we can really compute it. And this, I spare you the details, but basically from that you can easily compute now the rate of growth of from this probability you can compute this Krylov complexity or spread complexity as function of time, and you can compute how its time derivative or the rate of growth of this, and that gives us very sharp predictions for what this rate of growth of complexity should be in the holographic models at least. So basically at the zero temperature it should grow linearly with T proportional to this energy of the state, delta over E, times 1 over the epsilon, the smearing of the operator. At finite size, the rate of growth of the complexity should be periodic in time, and the L is basically the size of the CFT on which you do the computation. And finite temperature, we have an exponential growth of at late times, with the beta being inverse temperature of the black hole background. And here you can see this is exactly this picture I was advocating before. So this is the point particle that falls into a bulk. And you can see that indeed after the times where the particle reaches, if this is a description of the excitation by the point particle is true, you see that exactly at the time where the particle reaches the near horizon region, that's basically beta over 2 pi. That's where this complexity, the rate of the complexity starts to become exponential. Okay, perfect. And the question is, can we reproduce this from a gravity computation in ADS-CFT? And the way I defined for you this Krylov complexity, the way we compute it, the way we define it, is clearly basis dependence. So you might already complain here that, oh, how are you going to compare some basis dependent quantity in field theory on many-body system with something invariant in the bulk? And this might, already raise some general worries about general complexities, but also in particular this one. So I'll come back to this and show you that indeed we have such an issue. But let me do the computation of the momentum. So actually, basically what we need to do, what this radial momentum in ADS is just you take the point particle action, and this is given, this is parameterized on any of the geometry in terms of time, and then the radial direction is a function of time at fixed x0. This is exactly this picture I was showing for the local quenches. And basically by differentiating the Lagrangian with respect to r prime, you just compute what this momentum is as a function of time on the on-shell solution. So for example, for this Poincaré particle falling into the bulk, this is the action, and then we can compute the momentum in the z direction that has this form. And similarly, we can compute the momentum in the BTZ black hole, and we get this cosine hyperbolic 2 pi over t. So actually, if you remember my formulas, I was showing you at least this should correspond to this one, and this computation there should be some linear growth with time, and then there should be some exponential growth with 2 pi over beta t. Whereas here you see that something is off. Maybe at early time this would work out, but at late time definitely this goes to a constant. Whereas here it grows way too fast, and basically we are not getting a match. It's way too fast than the rate of growth of complexity. So you might be very disappointed, but on the other hand, you might say like, oh, there shouldn't be any matching. The quantity is not well defined, and maybe there's so many versions of complexity that maybe there's a better one that would do the job. Okay. So actually, you might be more persistent and take a different point of view, and maybe ask the question: is there actually a metric in the bulk that would somehow, that momentum in this matrix would reproduce all these three answers? Okay, maybe more phenomenological or pragmatical. And actually, the answer to this question is really beautiful. So you can check that if you take these three metrics and if you write them in the special raw coordinates, defined as basically the coordinate that is the proper distance, either from the black hole horizon or the center of ADS or Poincaré horizon, or a proper coordinate from the boundary, then basically if you take these three metrics, this is for finite temperature, this is for finite size, and this is for finite, this is for infinite temperature, this is for zero temperature or infinite line, and you compute the momentas, this is what you get. So they go as sine hyperbolic, they go as sine, they will be periodic, and they grow as t. And if you translate it, so now that I write for you again the rates of growth of complexity at zero temperature, at finite size, and I'm almost done, and finite temperature. If you translate mr to delta, what you're getting, that indeed the rate of growth of the spread complexity is precisely proportional to the momentum, 1 over epsilon momentum, but computed in the proper distance from the black hole, for example, for the finite temperature from the black hole horizon. Okay, so basically, this is the end of my talk. What I wanted to tell you today is that indeed we have a very sharp definition of complexity, namely the spread complexity in conformal field theories, that is proportional to the proper bulk momentum in ADS geometry, where by proper I mean computed in the radial coordinates that measure the proper distance to the horizon or to the center of ADS. And basically, this points that there might be a very deep connection between the Krylov basis, that is really a very particular basis in many body systems. For example, if we did the similar computation in energy basis, we would get completely different answers. But somehow, this Krylov direction in which we are computing might be related to a proper distance in the bulk. And of course, there's lots of generalizations of this computation that one can now study. For example, taking bug reaction, putting more operators, making the dictionary between momentum very precise. But in general, this points our, this kind of brings the elephant in the room that we should, in order to understand this better, we really need to understand holographic dictionary on the level of isomorphism between the boundary and bulk Hilbert spaces and how they are related. And there's also a relation to nice works of basically gravitational dressing, whether we can define these quantities in the bulk in some kind of, gauge invariant way. And this is all I wanted to say. Thank you. Thank you.
Time for a few questions.
Yes?
Here are first.
Hi. So, if I understand correctly, then a lot of this is dependent on defining time with respect to some boundary Hamiltonian. But if you had a case when you didn't have that, like in De Sitter, could you use your new way to define complexity, where you think of it as a radial momentum instead of time generated by some zero Hamiltonian?
Yeah, thank you for the question. I haven't thought much about De Sitter, but of course, you could run all these questions in parallel by computing momentas of various particles falling along slices of De Sitter, and then study what kind of growth of that momenta is generic and so on. Since I'm not that familiar with boundary models that we can really do computations, at the moment I don't have much to say. Maybe there are some claims about double scale SYK in various regimes that might be describing more like De Sitter physics, so maybe it's an interesting point there, but I haven't done the computation.
Hi, thank you for the nice talk. So I wanted to ask, you found some matrix whose momentum reproduces the rate of complexity. But now I guess that the interesting point is to understand if these matrices have some particular property or some nice feature related to black hole length. I don't know, is there some particular feature that you have seen in this matrix, and why, like if there is a relation between these three options in relation to the different bases? Thank you.
Yeah, so somehow, like when you think about metrics, the radial direction, you might get a bit lost. Like what is a nice way of defining it, and probably there's no unique way of thinking about it, except when you start defining metrics by simply saying that this radial direction is a proper distance to some point in the bulk. So I think this is a bit unique about this, and that's why. Maybe this relation to somehow gravitational dressing of a certain observable, maybe momentum in the bulk or making it gauge invariant, is related to that, but we are investigating what is special about that rho that measures the curl of complexity. Right.
Other questions? Yeah. It's more higher up there.
Was there anything about your CFT results that needed it to be holographic?
Sorry?
Did your CFT results do a large CF approximation or need any holographic properties?
No, as I said here, the main object is the return amplitude. So,
right.
So of course, this return amplitude is universally based on 2-point correlation functions.
But then isn't
of course, then the description in the bulk of a point particle of local quenches, of course, that only holds for holographic CFTs. So for example, if we take the CFT in some rational whatever model, like the point particle description of the quench and so on, this will not be valid. But of course, to really probe holographic nature of this computation, you have to do more complicated, for example, two operators, and then compute this curl complexity of two operators that will require 4-point functions for the return amplitude. So this to the match here, yeah, I agree. It's so far it's not super impressive because it's universal, but at least we really have the match.
Okay. And last question there.
So I wanted to ask, if there is a precise relation between this connection that you find between the growth of the Kirillov and the momentum, and the connection that was found in the work by Sonner between the volume and the complexity. So is it like one follows from the other?
I think their setup was different. It was just evolution of a thermofield double in SYK, double scaled SYK model and taking triple scale limits. So here we just do the CFT2 computation, and then the momentum is in ADS3. To my knowledge, I cannot easily derive one from the other, except that on holographic side, maybe there were papers I also mentioned by Jose Barbon and collaborators where they study momentum complexity correspondence. They had a claim, or maybe proof sometimes, that when the volume complexity equals volume in the bulk holds, then if you shoot some matter into the bulk, then the rate of growth of complexity in that holographic setup should be proportional to the momentum. But so maybe if this is really true, like there might be some kind of general way of linking to this. But my computations are purely CFT in terms of complexity. So I don't know yet what exactly. And I think we cannot repeat Julian's computation in 3 dimensions, right? I mean CFT2. So.
Okay, let's thank Pawel again then.